Multimodal CoT secrets, optimizing LLMs like never before. Have you ever wondered how humans effortlessly combine words and images to make sense of the world? Whether it's reading a map with directions or understanding a diagram with text, our brains excel at merging these inputs into meaningful insights. What if AI could do the same? Welcome to the revolution. Multimodal chain of thought. Multimodal CoT, where vision meets language for a groundbreaking leap in AI reasoning, with lessons drawn from cognitive science and philosophy. Introduction: the dawn of multimodal reasoning. AI has mastered single-modality tasks, reading text, analyzing images, but the real magic happens when we bring these two worlds together. Just as humans use text and visuals to solve problems, multimodal CoT combines vision and language, creating AI that reasons across both. Think of it as giving AI a pair of eyes to complement its brain. The core challenge. Small AI models, under 1 billion parameters, struggle with reasoning, especially when juggling text and images. Common pitfalls include hallucinated reasoning, which means that the model invents logic that doesn't align with inputs, and alignment failures, which means that visual cues and textual data don't sync, leading to flawed outputs. Tackling real-world multimodal challenges. Many real-world applications require multimodal reasoning. For example, interpreting patient symptoms alongside diagnostic imaging in healthcare industry, analyzing diagrams and accompanying explanations for intelligent tutoring systems in education field, generating context-aware captions or descriptions for multimedia content in entertainment industry, understanding spoken commands, visual surroundings, and contextual information to make decisions in the robotics industry. Multimodal CoT provides a robust framework for these scenarios by structuring the reasoning process, making it a critical tool for deploying AI in these practical applications. This is an example of multimodal CoT task from the research paper, addressing limitations of end-to-end models. End-to-end multimodal models, while powerful, often lack transparency and logical rigor. They may provide outputs that seem plausible, but are logically flawed because they rely on learned patterns instead of reasoning through the problem. Supporting ethical and explainable AI. In domains where decisions have ethical implications, such as autonomous vehicles, legal systems, or medical diagnoses, explainability is a legal and moral requirement. This is crucial for ethical compliance on ensuring decisions to be fair and based on logical grounds, and user trust on encouraging adoption by making AI systems more transparent and accountable. Facilitating knowledge transfer and training. Chain of thought, CoT reasoning, faces challenges in facilitating knowledge transfer and training due to its reliance on implicit knowledge within pre-trained models. It is highly dependent on task-specific prompt engineering, making it less scalable across diverse domains. CoT struggles with multi-step tasks that demand external knowledge integration and lacks feedback or self-correction mechanisms. Its training is constrained by the scarcity of annotated datasets with detailed intermediate steps. Additionally, CoT has limited interpretability in ambiguous tasks, making it harder to transfer reasoning frameworks to domains with nuanced or variable requirements. These limitations reduce its robustness and generalization across complex and dynamic problem-solving contexts. Why multimodal chain of thought, CoT, matters. Game-changing applications. Multimodal chain of thought, CoT, is crucial because it addresses the growing need for logical, interpretable, and accurate reasoning in tasks that involve inputs from multiple modalities, such as text, images, audio, or video. Traditional models often struggle with complex reasoning across diverse data types, leading to errors, inconsistencies, or non-interpretable outputs. Multimodal CoT provides a structured framework to overcome these limitations. Here's why it is particularly important: bridging logical reasoning across modalities. Multimodal tasks often require synthesizing information from different sources, such as understanding text in the context of an image or interpreting audio cues alongside visual data. Multimodal CoT explicitly models these steps, allowing the system to reason systematically across modalities. Without such a structured approach, models are prone to superficial correlations or misinterpretations, especially when modalities encode information differently. Enhanced interpretability. One of the core strengths of chain-of-thought prompting is its interpretability. When applied to multimodal data, CoT makes it possible to understand how the model arrives at a decision by breaking the reasoning process into intermediate steps. This transparency is particularly important for debugging to identify where errors occur in the reasoning process, trustworthiness for building user confidence by explaining outputs in domains like healthcare or autonomous systems, and accountability for providing clear rationales for decisions in high-stakes applications. Handling complex and ambiguous tasks. Multimodal tasks often involve high levels of ambiguity or complexity. In visual question answering, the question might be vague, requiring detailed analysis of both the image and the text to infer the correct answer. In autonomous robotics, a robot might need to interpret verbal commands while analyzing its environment. Multimodal chain of thought allows models to handle these complexities by explicitly reasoning through each modality and integrating their contributions logically. This reduces the likelihood of errors caused by overlooking critical details or failing to resolve ambiguities. Foundation, chain of thought method. The chain of thought method in large language models revolutionized complex reasoning by enabling models to generate intermediate reasoning steps before producing an answer. However, prior chain of thought research has largely focused on single modalities like language, neglecting the multimodal scenarios that combine text and images. Proposed solution, Multimodal CoT framework. To mitigate these issues, the paper proposes a two-stage multimodal CoT framework that separates rationale generation from answer inference. The first stage is called rationale generation. The model is tasked with producing a detailed reasoning chain based on the question and multimodal input. Both vision and text inputs are encoded and interacted with to ensure that the rationale incorporates relevant visual and textual details. The next stage is called answer inference. The generated rationale is appended to the original textual input. This combined input, along with the vision features, is then used to infer the final answer. This modular approach ensures that reasoning steps and final answers are independently optimized, reducing the chances of misleading outputs caused by flawed intermediate reasoning. Multimodal CoT isn't just a patch, it's a reimagining. With a two-stage framework, it separates reasoning from answering, optimizing each step for accuracy. Technical brilliance, the model architecture. The model is built upon a transformer-based architecture, consisting of the following steps. The first step is encoding. The text input is processed using a transformer encoder to create a textual representation. Vision features are extracted using pre-trained models like vision transformers and fused with text representation. The second step is interaction. Cross-attention mechanisms align the visual and textual features, allowing the model to understand correlations between modalities. A gated fusion mechanism is employed to combine vision and text representations effectively. The third step is decoding. The fused representation is passed through a transformer decoder to generate the target output, either a rationale or an answer. This is the overview of the model architecture from the research paper, Two-Stage Training. Stage 1 is where multimodal inputs generate a rationale. Stage 2 is where the generated rationale, combined with the input, leads to the final answer. Interdisciplinary foundation of multimodal CoT. Empirical evidence shows that structured reasoning techniques like CoT can significantly improve performance in tasks requiring logic or reasoning. Extending this to multimodal applications, CoT enhances the model's ability with cognitive science and philosophy foundation. For example, introduced by Alan Paivio in 1971, dual coding theory explains how humans process and store information using two interconnected systems. Also proposed by Philip Johnson Laird in 1983, the theory of mental models suggests that humans construct internal representations to reason about the world. By decomposing tasks into intermediate reasoning steps, multimodal CoT ensures that models focus on relevant features and maintain logical consistency, leading to more accurate and reliable outputs. The results: breaking records and setting standards. The framework was tested on multimodal benchmarks, such as ScienceQA and AOKVQA, which evaluate reasoning over questions that combine text and images. Multimodal CoT achieved state-of-the-art performance on Science QA, outperforming models with significantly larger parameter sizes. This underscores its efficiency and scalability. By incorporating visual information, hallucinated rationales were reduced by 60.7%, resulting in more accurate and reliable outputs. The integration of vision features boosted learning efficiency, allowing the model to converge to high accuracy within fewer training epochs. This is the resulted performance comparison from the research paper challenges. Multimodal chain-of-thought reasoning is a powerful approach to improving logical consistency and interpretability in multimodal tasks. However, its implementation and application are accompanied by several challenges. These challenges arise due to the complexity of multimodal reasoning, the limitations of current models, and the need for sophisticated integration across modalities.
Modality alignment and integration. Multimodal CoT requires models to align and integrate information from different data types, like text, images, and audio, which vary in structure and abstraction. Misalignment between modalities can result in reasoning errors or superficial connections, challenging the synthesis of meaningful cross-modal insights. Computational complexity. Multimodal CoT significantly increases computational demands due to the need to process large-scale multimodal inputs, generate detailed reasoning steps, and integrate cross-modal information. This makes scalability and real-time applications challenging, especially for resource-constrained environments. Lack of ground truth reasoning chains. Training and evaluating multimodal CoT requires datasets with clear and accurate ground truth reasoning annotations, which are often unavailable. This hampers the ability to supervise models effectively and assess their reasoning quality. Evaluating multimodal CoT. Assessing the quality of reasoning chains across multiple modalities is complex and subjective, as it involves evaluating logical consistency and cross-modal coherence. Poorly defined metrics make it difficult to benchmark and improve these systems. Error propagation. Mistakes in early reasoning steps can propagate through the chain, particularly in multimodal tasks where errors in one modality, e.g., misinterpreted image features, affect subsequent reasoning. This reduces the reliability of multimodal CoT outputs. Real-time application constraints. Generating detailed reasoning chains often introduces latency, making multimodal CoT less suitable for real-time applications like live video analysis or autonomous driving, where immediate responses are critical. While multimodal CoT offers significant advantages in enhancing logical reasoning and interpretability across modalities, it is hindered by challenges such as modality alignment, computational complexity, data scarcity, and evaluation difficulties. Addressing these challenges requires advances in architecture design, efficient training strategies, and the development of high-quality datasets with annotated reasoning steps. By overcoming these barriers, multimodal CoT can unlock its full potential for a wide range of applications, from healthcare to autonomous systems. Future of multimodal CoT, XI. Multimodal chain-of-thought reasoning can play a significant role in advancing explainable AI by enhancing the interpretability, transparency, and accountability of AI systems that operate across multiple data modalities such as text, images, audio, and video. Here's how it contributes to XI. Step-by-step reasoning for transparency. Multimodal CoT breaks down the reasoning process into intermediate, interpretable steps for each modality, making the decision-making process more transparent. By explaining how a model processes text, images, or other inputs at each stage, it provides insights into what information was extracted and how it contributed to the final output. For example, model diagnosing a condition based on X-ray images and patient history could use CoT to explain how specific visual features in the X-ray and symptoms in the text were combined to make the diagnosis. Cross-modal alignment for interpretability. Multimodal CoT ensures that outputs from different modalities are logically aligned and contribute meaningfully to the final result. This explicit integration of reasoning steps across modalities makes it easier to trace the connections between inputs and decisions. For example, if asked, "What is the person holding in the picture?" the process might involve
identifying objects in the image, mapping the textual query to the image features, and synthesizing the answer. This decomposition allows users to understand the logic behind the answer, enhancing trust. Error traceability. By articulating intermediate steps, Multimodal CoT makes it easier to identify where errors occur in the reasoning process. This can be invaluable for debugging and improving AI systems. For example, if a system misinterprets a road sign due to poor image analysis, the reasoning chain could highlight this specific error, allowing developers to address the issue without retraining the entire system. Justification of decisions. Multimodal CoT allows models to justify their decisions by explicitly showing how they reason through inputs. This is critical in domains where decisions have significant consequences, such as law, finance, or medicine. For example, a model summarizing legal documents and making recommendations can use CoT to justify its conclusions. Handling complex scenarios. Multimodal CoT enhances explainability in complex scenarios where one modality alone cannot provide sufficient insight. By showing how information is synthesized across modalities, CoT addresses challenges where decisions rely on subtle cross-modal interactions. For example, detecting fraud based on transaction data, customer emails, and surveillance footage requires reasoning chains to explain how anomalies were identified across these inputs. Addressing bias and fairness. By explicitly documenting reasoning steps, Multimodal CoT can reveal biases in the model's decision-making process. For instance, if a model overly relies on certain visual features or textual phrases, these tendencies become apparent in the reasoning chain, enabling corrective action. For example, a recruitment system evaluating resumes and video interviews could use CoT to show how it ranked candidates, helping uncover biases in either modality. Future of Multimodal CoT, computer vision. Multimodal chain of thought has significant potential to advance computer vision by enhancing the reasoning, interpretability, and integration of visual data with other modalities. Computer vision tasks often require contextual understanding that goes beyond visual analysis, such as aligning visual inputs with textual descriptions, understanding spatial temporal relationships, or reasoning about visual scenes. Multimodal CoT enables these capabilities by introducing step-by-step reasoning across modalities, leading to improved performance and explainability. Here's how Multimodal CoT contributes to CV. Enhanced scene understanding. Multimodal CoT facilitates detailed reasoning about visual scenes by combining image or video analysis with textual or other contextual inputs. It allows models to generate intermediate reasoning steps that explain how specific visual features relate to overall scene comprehension. Improved visual question answering. In VQA tasks, where a model must answer questions about an image, Multimodal CoT provides a step-by-step reasoning framework that integrates visual features with the semantic structure of the question. This structured reasoning reduces errors caused by shallow pattern recognition, multi-step object detection, and localization. CoT reasoning allows CV models to perform object detection and localization in a multi-step, interpretable manner. By explaining how features like shape, color, and spatial arrangement contribute to the detection of objects, CoT improves transparency and accuracy. Context-aware image classification. Image classification tasks often rely on contextual clues in addition to the object's primary features. Multimodal CoT enables the inclusion of context by reasoning about relationships between detected objects, their environment, and external textual or numerical inputs. Explainability in vision applications. One of the biggest challenges in CV is the lack of explainability, especially in tasks like medical imaging or autonomous driving. Multimodal CoT addresses this by breaking down the model's reasoning into human interpretable steps. Support for temporal reasoning in videos. For video tasks, such as action recognition or event prediction, CoT can reason across frames, describing how temporal relationships evolve over time. This makes it particularly useful for tasks like video captioning or anomaly detection. Multimodal scene graph generation. Scene graph generation involves creating a structured representation of a visual scene by identifying objects and their relationships. Multimodal CoT can enhance this process by combining visual analysis with external textual knowledge or reasoning. Robustness to ambiguous inputs. When visual inputs are ambiguous or incomplete, Multimodal CoT allows models to reason through alternatives by leveraging complementary modalities like text or external data. This increases robustness and reliability in uncertain scenarios. Multimodal chain-of-thought reasoning enhances computer vision by introducing structured, interpretable reasoning that integrates visual data with other modalities. It supports applications like scene understanding, VQA, video analysis, and robotics, while improving explainability, accuracy, and robustness. By enabling step-by-step reasoning, Multimodal CoT allows CV systems to tackle complex, context-rich tasks with greater transparency and reliability, making it a key innovation for advancing the field. As we stand on the threshold of a new era in artificial intelligence, Multimodal Chain of Thought, CoT, marks a paradigm shift, pioneering reasoning that feels almost human. Whether it's enhancing healthcare diagnostics, creating intuitive robots, or advancing education, the possibilities are boundless. But this journey is just beginning. Imagine a future where AI doesn't just answer questions, but truly understands the world it interacts with. Multimodal CoT isn't just a technical leap. It's a step toward AI that collaborates, learns, and transforms how we solve the most complex problems. What's your next step? Share your thoughts in the comments below. Hit that like button if this blew your mind, and subscribe for a deep dive into the tech shaping our future. See you in the next video.